So, welcome all. So, we will continue from the last time. We were discussing stress wave propagation. Okay. So, we have seen the propagation of the longitudinal waves, shear waves, transverse waves. Okay. So, we will continue from that. Okay. So, we will be talking about the elastic waves today. Okay. So, different types of elastic waves can propagate in solids. Okay. And they depend upon how the motion of a point in the solid material is related to the direction of the propagation of the wave. Okay. So, the primary elastic wave is usually referred to as the longitudinal wave. Okay. So, under uniaxial stress conditions, okay, that is a elastic wave travelling down a long slender rod. Okay. So, if this is a rod, okay, or if we are mimicking it as a spring. Okay. So, the wave propagation, direction of the wave propagation is in the same lines as in the direction of the stress. Okay. So, these are the elastic waves. Okay. So, the wave propagation speed is given by C naught, okay, square root of E over rho, where E is the modulus of elasticity and rho is the density. Okay. So, this is a one dimensional approximation, okay, of the elastic of the wave propagation speed. Okay. So, for a generalized 3 dimensional case, some additional components will come into picture. Okay. So, the more general expression is given by this equation, okay, for a 3 dimensional case. So, the longitudinal wave, okay, so this is the primary elastic wave, okay, and the secondary elastic wave is referred to as the shear wave, okay, or the distortional wave. Okay. And here it travels perpendicular to the direction of the wave propagation. Okay. So, the motion of particles is in the transverse direction, okay, and the wave propagation is in the horizontal direction, okay, whereas in the longitudinal waves both are in the same direction. Okay. And shear wave velocity is given by, again here it was given by the modulus of elasticity and here it is being given by the shear modulus. Okay. So, these are the two types of elastic waves, longitudinal waves and the shear waves. So, other form of elastic waves is called the surface waves, okay, or Rayleigh wave, and there are interfacial waves and flexural waves also present in case of 2 dimensional objects, okay, such as plates and all. Okay. So, these are the major components of the elastic waves: longitudinal waves, shear waves and the surface waves, okay, and sometimes bending waves are also present. Earlier we were dealing with the elastic waves, now plastic waves. So, plastic or inelastic, meaning permanent deformation is being caused in this type of wave propagation. Okay. So, plastic deformation takes place in ductile metals, okay, when the stress in the metal exceeds the elastic limit. Okay. Once the induced stress is more than the elastic limit, or if sigma y, the value of sigma y is exceeded, okay, then the plastic deformation will take place. Okay. So, under dynamic loading condition, the resulting wave propagation can be decomposed into elastic and plastic regions. Okay. So, there will be a elastic region and there will be a plastic region. Okay. So, under uniaxial strain conditions, the elastic portion of the waves travels at the primary longitudinal wave speed. Okay. So, C naught equals to root over E over rho, as we have seen previously. Okay. So, this will be the elastic longitudinal wave, okay, while the plastic wave front travels at a local velocity, okay, where the local plastic deformation takes place. So, the plastic wave will travel at the local velocity. Okay. For an elastic perfectly plastic material, the plastic waves travels at slower velocity than the primary elastic waves, okay, and that will be given by this equation. Okay. Okay. Moving ahead. So, shock waves. Okay. So, typical stress strain curve for a ductile material and under uniaxial stress and uniaxial stress conditions are given below. So, this is a uniaxial stress and this is the uniaxial strain. Okay. So, under uniaxial stress conditions, the tangent modulus of the stress strain curve decreases with strain. Okay. It means that as this is increasing, this tangent modulus, okay, will keep on decreasing. Okay. the plastic wave speed therefore decreases at the as the applied jump in the stress associated with the stress wave increases. Okay. So, under these conditions there is an unlikely chance that the shock waves are created. Okay. Under uniaxial strain conditions, okay, the plastic modulus, okay, that is AB increases with the magnitude of the applied jump in stresses. Okay. So, if the stress jump associated with the wave is greater than the gradient, okay, if this gradient becomes, okay, if the jump is more than this gradient, then the plastic wave will travel at a higher speed than the elastic wave. Okay. Since the plastic deformation must be preceded by the elastic deformation, then the elastic and plastic wave coalesce and propagate as a single plastic shock wave. Okay. So, this will give rise to a shock wave during a plastic wave. Okay. So, a shock wave can be considered to be a discontinuity. Okay. Normally, it is regarded as a discontinuity in material state, okay. Density, energy, stresses, plastic velocity, okay, which propagates through a medium at a velocity equal to the shock velocity. Okay. So, the propagation velocity is equal to what is known as the shock velocity, okay, and there is a discontinuity in the two regimes, okay, and this is the interface. Okay. So, relationship between the material state across the shock discontinuity can be derived using the principle of conservation of mass, momentum and energy. Okay. So, these are known as the Huguenot equations and they are given by this formulation. Okay. Okay. So, impact loading and shock response. So, impact loading is a sudden short duration load applied over millisecond, okay, meaning there will be a large force and the application of the force will be applied in a very short duration of time, typically in the millisecond range. Okay. So, the collision will start, maximum force will be attained and the collision will end. Okay. So, it causes rapid acceleration and high stress gradients. Okay. Shock loading. So, this is an extreme form of dynamic loading with near instantaneous force application. It produces shock waves, localized high pressure zones and even phase transformation in material. Okay. Especially in metals and ceramics, there can occur phase transformation due to the application of the shock loading. Okay. And this phenomena can be used in different applications. Okay. So, using shock loading, okay, in different practical applications, okay, instead of doing it in the conventional way, different type of applications can be done. Okay. So, response of a ductile material. Okay. A ductile material such as steel, copper, aluminum. Okay. So, ductile material absorb energy through plastic deformation. Okay. They redistribute the stress and the likelihood of the fracture. Okay. So, as SRS increases, okay, so in this ductile material the redistribution of the stresses also increase and that ductile material, as we have seen earlier, they are ideal for energy dissipation in structures, okay, and they can be used in the glass boxes, barrier systems and other protective panels. Okay. So, continuing ahead. So, impact loading and shock response in ductile material involves complex material behavior, which we have seen earlier, and it is also accompanied by large plastic deformation. There is a damage mechanism, okay, and fracture takes place under extremely rapid and intense loading conditions. Okay. So, understanding and modeling this responses, okay, it requires experimental as well as different types of theoretical approaches. Experimental approach in order to characterize the material behavior, theoretical approach to use this develop constitutive equations to be used in the application of the dynamic equations. Okay. And then microstructural behavior, microstructural damages, phase transformation and other effects also needs to be accounted in order to get a overview and a complete behavior of the structure also. Okay. So, physical mechanism under impact and shock, plastic deformations, okay, this we have seen already. Okay. Then damage evolution. So, damage evolution under shock and impact loading, the damage evolution includes the void nucleation, which we have seen, growth and coalescence. Okay, we have seen this thing, okay. And this thing ultimately leads to the microstructural damage and fracture. Okay. So, this process is influenced by loading path. Okay. This type of microstructural damage and fracture is greatly influenced by the loading path and intensity, the material microstructure and purity. Okay. Purity means if there are more and more defects, this damage evolution becomes unpredictable. If it is more pure, that is the grain size distribution is uniform, the percentage of impurity is less, then the damage mechanism and the fracture mechanism is a bit controlled. Okay. It depends upon the strain rate sensitivity, okay, and also depends upon the initial and the final dynamic tensile stresses, okay, occurring during the wave application of the shock waves. Okay. So, the behavior under fracture and failure. So, under sufficiently high shock intensities, dynamic fracture can initiate, but it will depend again upon the purity, upon the microstructural configuration, okay, the amount of grain size and other factors. And other failure, either ductile failure will be happening if this criteria are met of high purity and application or availability of low microstructural damages, or failure can also occur through localized damage zones culminating in the complete separation. Okay. So, it will also depend upon the microstructural behavior of the metals also. So, experimental approach. So, there are different types of experiments available in order to characterize this failure modes. Okay. So, in the plate impact and flyer plate experiments, okay, a planar shock wave in metal alloys is applied, okay, and the dynamic responses are observed, okay, such as free surface velocities, the damage pattern and fracture evolution. Okay. So, after that dynamic loading of plates and beams can also be done. So, experimental setups with rigid mass impacts on clamped metal plates, okay, like we have some metal plates, okay, and we can clamp it from all the sides, and some rigid mass, okay, can be dropped on these plates. Okay. So, and the permanent transverse displacement and the ductile deformation pattern, okay, without failure and at low impact energies can be observed. Okay. So, what is done is that in this type of plates which are clamped at all the ends, okay, a rigid mass is dropped and it is such designed that the permanent failure does not occur and only the transverse deformation is recorded. Okay. So, characterization techniques. So, in order to do the measurement, okay, different types of techniques can be used: optical metallography, electron black scatter diffraction, tomography, okay, basically to measure this damage. Okay. This type of measurements can be done. Okay. So, the idea is to test different types of configurations, okay, and see the distribution of the stresses, the distribution of the displacement, and characterize the behavior of the material under different dynamic conditions. Okay. And now, using the data from the experiments, the constitutive models can be made, okay, and this models along with the combining them with the information about the damage propagation, information about the microstructural formation, information about the grain size, porosity, and using all these factors, the continuum damage models, okay, or the damage models for the continuous surface can be developed. Okay. So, this developed models, these are based on the physical evolution of porosity, wide nucleation growth and the damage accumulation using constitutive laws. Okay. What is the meaning here is that the propagation of the damage, okay, follows some experimental validation, okay, where different type, where in the experiment the data obtained from the experiment is related back to the basic parameters, okay, like stress, strain rate, grain size, okay, the propagation of the damage and other phenomena, okay, and a constitutive model, okay, or a basic model relating the stress with all these phenomena is developed, and this is used to understand the behavior of the different configuration in the dynamic loading case. Okay. So, some of the readily available constitutive models are, a lot of constitutive models are available. So, one is outlined here, that is the Gerson-Tvergaard-Needleman model. Okay. So, these things can again be put into different analytical tools like finite volume and extended finite element methods. Okay. So, using finite volume method or the finite element method. So, this constitutive models can be used to do a simulation and understand the behavior of the structure during a dynamic event. Okay. So, this requires advanced computational framework. Okay. This requires high speed computers, okay, which can handle a lot of heavy calculations. Okay. And since earlier we have also seen that the mesh size should be very small and the time stepping also needs to be very small. Okay. So, the time step required and the mesh size is very small, that is why this advanced computational frameworks are required. Okay. For example, some sort of supercomputer will be required in order to carry out the whole dynamic simulation. Okay. And this type of phenomena like dynamic fracture, okay, with cohesive modeling. Okay. So, this type of things has to be put into the finite element methodology, okay, in order to study the behavior of the devised parameters, okay, in order to study the behavior of the materials under dynamic loading. Okay. Shock wave propagation modeling. Okay. So, what is done is that in shock wave propagation modeling, so equation of state. Okay. So, sometimes the constitutive modeling is difficult. Okay. So, instead of doing a constitutive modeling, the equation of state is modeled, okay, and numerically, okay, using von Neumann artificial viscosity or some other formulation is used to model the distribution of the pressure density and the internal energy changes across the different regime. Okay. And this is done using the equation of the state modeling. Okay. And the material modeling can also be made using the theoretical rigid plastic analysis assumptions also. So, it can predict ductile plate deformation under impact, and it also can account for large transverse displacements, boundary condition and energy dissipation through plastic hinges. Okay. So, this type of formulation can also be used to predict the behavior of the system. Okay. So, these are the some of the challenges, these are some of the steps that are required in order to model the different conditions, like modeling the continuum damage models for the material behavior, putting them into the finite element methodology and capture the different behaviors, model the shock wave phenomena using equation of states, and some simplistic theoretical models can also be used. Okay. So, each and every sphere requires some sort of experimental data also, and then some sort of model validation also. So, after learning all these things, what are the key findings and how it can be used? Okay. So, ductile metals exhibit a progressive form of failure, okay. So, which might include void nucleation to fracture, okay, under increasing stress levels. Okay. So, the models needs to account for both microstructural effects and microscopic responses to effectively stimulate the shock induced damage and predict failure. It means that the grain size distribution, okay, the effect of the temperature, the amount of impurity and the increase in the toughness, increase in the energy absorption capacity, all these things needs to be properly accounted for in order to model the behavior of the material under high rate of loading. Okay. Then impact experiments needs to be done, okay, from different types of impact tests, okay, to study the deformation pattern, okay, and to study the evolvement of the failure pattern. Okay. And these things should be predictable by the theoretical rigid plate models. Okay. So, the experimental data should be used in order to support the development of the theoretical models. Okay. Shock wave loading rates influence the deformation pattern, okay, whether it is going to be a ductile type of failure or it will go into a brittle like fracture regime. Okay. So, the modeling of the shock wave is also important, okay. And the behavior of newer materials, okay, like viscoelastic polymers, okay, or electromagnetorheological fluids, they are also employed in shock wave mitigation by the absorption of the energy dissipation. Okay. So, all these things needs to be studied in order to devise an energy absorbing material. Okay. So, as the course progresses, we will be dealing into the finite element simulation also. Okay. So, that this type of things are studied and exhibited, and we get our hands on experience upon this types of applications. So, different aspects of the loading. Okay. So, shock loading is a high strain rate dynamic loading, and it generates pressure waves. Okay. Plastic deformation, okay, it is a large irreducible strain within ductile materials. Damage mechanisms, so different types of damage mechanisms are outlined: wire nucleation, growth, collisions, spalling, fractures, and so on and so forth. Okay. Experimental setups: plate impact facility, flyer plates, velocity measurements, SPH, and so on and so forth. Okay. Modeling method, okay, damage models, finite element method, finite volume method, constitutive laws, okay, material response influences, okay, microstructure, strain rate, loading path, equation of state, boundary conditions, and practical applications. Okay. So, these are the different aspects, okay, which needs to be studied, okay, for the high strength loading. Okay. So, under impact loading or blast loading, these aspects needs to be properly catered with, they needs to be properly analyzed, studied, and their values validated with the experimental data, and then incorporated into the constitutive models, put into the finite element model, and then get the simulation properly, and then application of all these things combined, into some practical application to have a safety design and to select the or to optimize the materials and to devise the proper mitigation technique. Okay. So, these are the different aspects that needs to be catered for this type of loading. Okay. So, observations of the dynamic yield strength. Okay. So, some of the factors we will be looking into and how does it varies. Okay. So, yield strength increases with the strain rate. Okay. So, that we have seen. Okay. As the strain rate increases, the yield strength is going to increase. Okay. So, at higher strain rate, material resists plastic deformation more strongly. Okay. So, this behavior is crucial in designing components subjected to impact, crash, or explosive loading. Okay. So, why it matters? It matters because the prediction of the yield behavior under dynamic loading is essential for the crashworthiness design. Most of the design parameters are dependent upon this yield criteria. So, this will help in designing of the high impact resistance structure, and this also helps in the high speed forming process. Okay. And this is a key factor that is used in the finite element simulation. Okay. So, we should have a good idea of how this yield strength, okay, varies, how this yield strength varies with the increase in the strain rate. Okay. So, why does the yield strength increases with strain rate? Okay. Why does it happen? It happens because there is a dislocation motion, and this dislocation motion becomes more difficult at high strain rate. Okay. So, when we are going into the yield regime, okay, so the dislocation of the particles has to occur. Okay. And as the strain rate is increased, so achieving these things becomes more and more difficult. Okay. So, that is why it requires higher amount of energy. Okay. That is why the yield strength becomes more. Okay. So, there is a less time for thermal activation and recovery, and the material affects stronger and stiffer. There is the increase in the Young's modulus also. Okay. So, typically if you see for a quasi static loading, okay, if it is exhibiting a yield strength of around, let us say 250 MPa. So, in case of dynamic loading, okay, it may exhibit increase in the yield strength of around 400 to 600. Okay. So, it can increase more than 2 times also. Okay. So, depending upon the rate of loading, the yield strength can be twice also, okay, or even more than twice also. Okay. So, there is a significant increase in the yield strength. Okay. So, that is why modeling the yield strength and getting a good estimate of the yield strength is very crucial in the dynamic analysis. Toughness. So, we talked about yield strength, now we are looking into the toughness. Okay. So, we are looking into the fracture toughness. What is toughness? The toughness is the ability of a material to absorb energy up to fracture, meaning the area under this curve, okay, gives an estimate of the total amount of absorbed energy. So, more is this area, more is the toughness. Okay. So, it represents the total energy per unit volume before failure. Okay. So, this is basically an integral of the stress strain per unit volume. Okay. So, this is nothing but energy per unit volume. Okay. So, this is visualized as the area under the stress strain curve. Okay. So, what are the mechanism behind toughness? Okay. So, there is plastic deformation. Okay. So, the mechanism, okay, from elastic to plastic, it also includes the microvite nucleation, growth process and the coalescence process. Okay. There are rough fibrous fracture surfaces, okay, and the energy consumption during slow crack propagation. Okay. So, depending upon the different type of failure, okay, different type of energy absorbing mechanisms comes into play. Okay. So, ductility. Okay. What is the relationship between toughness and ductility? Toughness, ductility and strength. Okay. So, the ductility is the extent of the plastic deformation before fracture. Okay. How far it can go. Okay. Okay. So, the change in length versus the original length will gives us an idea about the ductility. Strength, maximum stress that the material can withstand. Okay. So, depending upon which stress we are looking into, the yield stress or the ultimate stress. So, this is the maximum stress that the material can withstand. Okay. So, one is in the x axis, one is in the y axis. Okay. So, ductility lies in the x axis, strength lies in the y axis. Okay. Now, toughness is a combination of the strength and ductility both. Okay. So, remember it is the representation of the area under this curve. Okay. So, this is an x plus y factor. Okay. It incorporates both the ductility as well as the strength factor. Okay. So, if either one is low, okay, it will affect the toughness also. Okay. So, this is not an independent measure, but this is a combined measure of the strength and the ductility both. Okay. So, how can we measure the toughness? We can measure the toughness using Charpy or Izod testing. Okay. Basically, what we used to do is that we used to keep a notched specimen, okay, and there was a swinging pendulum, okay, and we used to measure the total amount of energy required in order to cause this straight away fracture. Okay. So, using a Charpy or an Izod impact thing, we used to get the total estimate of the energy required to fracture this surface. Okay. We can do tensile test, okay, and the area under this tensile test will also gives us an estimate of the toughness. And in a tougher material, okay, the area under the stress strain curve will be more, okay, signifying that more energy is absorbed during this entire process. Okay. So, moving ahead. So, the measures of the fracture toughness. So, the fracture toughness, okay. So, this is the resistance to the crack propagation and this is essential for the reliability of the structure. What is the effect of the dynamic loading? Okay. Due to the possible ductile to brittle transition, the crack velocity increases significantly. Okay. So, shift in the material behavior. Okay. So, if there is a less plastic deformation, there is a more abrupt failure and this is sensitive to strain rate and temperature. Okay. What are the measurement methods? Okay. As we have seen, Charpy or impact test and high speed fracture test with pre-cracked specimen can be used to measure the fracture toughness. Okay. What is the engineering relevance? It is essential in designing of the crashworthiness, plastic protection, aerospace structure. So, any type of protection, it will require an estimate of the fracture toughness. Okay. So, this is a representation of the formation of the crack. Okay. So, this is a microstructural representation, and here the formation of the crack is shown. Okay. So, KIC given by the equation is a measure of the fracture toughness, okay, where sigma is the engineering stress, A is the crack length, okay, and Y is the geometric factor. Okay. So, using this properties, the fracture toughness can be categorized. Okay. So, these are the different forms of fracture, okay, where the opening is required. Okay. So, this is failing, okay, in the opening mode. Okay. So, in plane shear mode is there. Okay. So, this guy is going inside and this guy is moving like this thing. Okay. So, this is the in plane shear, and if it is moving across the plane, so this is the out of plane shear. Okay. So, these are the different types of failure in case of fracture. Okay. So, we will stop here today and we will continue from the next time. Thank you.